In this video, we're going to introduce what we call effect sizes in statistics, and then we're going to talk about the confidence interval, both of which correspond with the independent samples t-test. So let's start talking about effect size. When we conduct a independent samples or a two sample t-test, we're studying or evaluating statistical significance, right? Statistical significance tells us whether a difference exists or not, right? Is this difference large enough to rule out chance? All right. Even in cases where there is statistical significance, it doesn't mean that there is also practical or meaningful significance, right? So statistical significance doesn't tell us how meaningful or important that difference that we may see in those two groups, how important the differences are, right? That is where practical significance comes into play. Practical significance helps to determine whether the difference is large enough to make a real world impact. All right. We'll be honest here. Sometimes based solely on sample size, right? If our sample size is really large, it's going to be easier to detect differences compared to if our sample size is small. So this is going to be especially important for studies where our samples, our two groups, are really large. Like let's say in the 500s, right? We'll probably more easily be able to see statistical significance, even when the difference between the two group means are very small. That is where our effect size measure comes into play. The effect size measure, or in general, an effect size is a standardized measure that quantifies the strength or the magnitude of the differences that we may see in whatever we're studying. And of course, in the two sample or the independent samples t-test, we're studying the differences in those group means. So our effect size will quantify the strength or the magnitude of those differences. The specific statistical index that's used when we use an independent sample t-test is the statistic known as Cohen's d. So Cohen's d, is a measure of effect size for the independent samples t-test, which is measured in standard deviation units. There are a couple of formulas for Cohen's d. One is when that assumption of equal variances or the homogeneity of variances is satisfied. Cohen's d is given by this formula to the left: x bar sub 1 minus x bar sub 2 divided by the pooled standard deviation. Remember, when we use students t test, we use the pooled variance in order to help us get the standard error of the difference in the means, right? But this denominator is the standard deviation, the pooled standard deviation, not the pooled variance, because it is in standard deviation terms or units. All right, so that's the formula when we assume that the equal variances is true, right? If we have unequal variances, remember we use Welch's t-test in that case, then our formula for Cohen's d is this. It's the difference between those sample means divided by the square root of the sum of the variances divided by 2. All right, the sum of the sample variances divided by 2. All right, and so this is what we use as Cohen's d when we have Welch's t-test. This is what we use when we have students t-test, right? What's nice about this is that our statistical software is automatically going to give us the correct Cohen's d, and so that we don't have to really think about adjusting a formula. All right. Now, of course, because this is a difference in the numerator and the denominator is a standard deviation in the square root of some sums that involve variances, the numerator, the sign of the numerator is going to basically tell us the sign of Cohen's d, right? So if Cohen's d is positive, that means that the first group was larger than the second group mean, right? That means group 1 performed better, had the larger mean. And if Cohen's d is negative, that means the second group had the higher mean. I use perform better here. I guess had the higher mean or larger mean will be the better terminology here. All right. Either way, when we're interpreting Cohen's d to get the effect size, we kind of have some standardized rules of thumb that the field has kind of followed. And it's these here. If I get the absolute value of Cohen's D equaling to zero point 0.2 or less, then we have a weak effect. A moderate effect is a D of 0.5. So if I don't get to 0.5, I'm going to call it moderate. I'm going to call it weak. All right. And once I get to 0.8, I can call that effect strong. So anything greater than 0.8 is strong. If it's not the 0.8, I'm not going to use the term strong. 0.5 is moderate. If it doesn't get to 0.5, I'm going to call it I'm not going to call it moderate. And then 0.2 is weak. So if I get a 0.4, that's still a weak effect. It's getting weak to moderate, but that's still considered a weak effect. And so let's look at how we can calculate or actually use JASP to calculate the effect size measure for that diesel versus gasoline bus example that we did in our last video. I'm going to go to JASP. This is where we left off in JASP during our last lecture. We had the independent t-test. We saw that we could assume that the variances were equal so that we use student t-test. Alternative hypothesis was that the diesel group drove fewer miles on one tank compared to the gasoline group. So that was our alternative. If I want to add Cohen's D under the additional statistics here, I have effect size. Remember, that's going to tell me about practical significance. So just because, well, even in this example, I don't have a significant difference here, and so I shouldn't see a big effect. But if I especially had a significant p-value, one that's less than 0.05 or whatever alpha that I'm using, I definitely am going to want to report the effect size. There are multiple effect sizes for what we're going to be doing. Cohen's D is good enough for us. Once I do that, I see that my independent samples t-test results have expanded to include information about Cohen's D. The value of Cohen's D based off of our sample is this negative 0.158 here. And so if I go back to my notes, I have my value of Cohen's D of negative 0.158. Remember, we said that the absolute value of D, if it's around 0.2, that is still considered a weak effect size. And so since it's smaller than that, I know it's a weak effect, right? So I have an interpretation here of the effect size. It says an effect size of D equals negative 0.158 suggests a small negative difference between diesel and gasoline buses, right? With gasoline buses averaging slightly higher mileage compared to diesel buses, right? Remember, we said that if it's negative, group 2 did a little bit better. And so since group 2 in this case is gasoline, this is why this part says gasoline averaging slightly higher mileage on one full tank of gas compared to diesel. And how much higher on average? About 0.158 standard deviations higher. Though that difference is not practically significant, since that is a weak effect size. In addition to reporting the effect size, we also can report a confidence interval from mu1 minus mu2. All right. If you recall, all of our confidence intervals are in the form point estimate plus or minus a critical value times your standard error. Our point estimate, when we're looking at the difference in our population means, is the difference in our sample means, right? So this is our point estimate here. Our T statistic is our critical value is coming from a T distribution, right? Notice I put this alpha over 2 because it's looking at the two tails of this distribution. So for instance, if I were going to do a 95% confidence interval, right? Then the middle area that I don't have shaved under this curve represents the 95%. This alpha represents the other percentage, right? Which is in those tails. And so since the t distribution is congruent, that's why we have the alpha divided by 2, right? So that 5% or 0.05 divided by 2 is 0.025. So this area here is 0.025 and this area here is 0.025 if we want to do a 95% confidence interval, right? And so we could use a function in R or in JASP, like sort of like our Q norm, if you remember that from before, but now it's a T distribution, so it's a QT function in JASP. We're not going to do all of that because our confidence intervals are going to be given to us, but basically I can find this value here or this value here in the upper tail, knowing that this area up here is 0.025, and that means the area below it is 0.975. All right, so that T is going to be replaced by this value here. You can do it with the negative as well, and you're going to get the same values. And then we have our standard error of our difference in our sample means here, x bar 1 minus x bar sub 2, right? So that's going to be our confidence interval. Now, I do want to make a note here. This is a two-sided confidence interval. That means we're getting a lower bound and an upper bound because we're going to be given two values here. So this is a two-sided confidence interval. You can, if your alternative hypothesis is one-sided, that means it's either a left-tailed alternative or a right-tailed alternative, you can create a confidence interval that is one-sided. But generally, for what we're going to do in this course, we're going to construct two-sided confidence intervals. But do know that one-sided confidence intervals do exist. And so what I want to do is I want to go to JASP and show you how you can construct a confidence interval. This is the same menu that we saw when we were looking at Cohen's D just now, right? Well, if I go under the menu that says additional statistics, there's a location parameter, right? So I can do that. And if I want to get a confidence interval, I'm going to click on confidence interval. And then I can change the percentage. Well, what we're going to do is we're going to construct a 95% confidence interval. That's the confidence level that's most often used in social sciences, especially education. And so as you can see, I have my mean difference, x bar 1 minus x bar 2 here. And notice here, now note here, my alternative hypothesis says less than, right? So JASP is going to give you the confidence interval that aligns with your alternative hypothesis. It is one-sided, all right? And this confidence interval, given that it is one-sided, it's not going to be as, well, it's infinitely wide, okay? But the bounds of that confidence interval is not going to be as wide as it can be, which is why we're going to use a two-sided confidence interval. And this two-sided confidence interval here, in order to get that, I'm going to use not equal to, all right? When I do that, I get a lower bound of that confidence interval and an upper bound of that confidence interval, all right? Again, we're going to stick to these two-sided confidence intervals because it's going to give us a good measure of how small our difference might be and how large it might be, instead of just focusing on if we had a less than, how large it can be, so on and so forth. All right. So when I do the confidence intervals, I'm going to go back to the not equal here. Otherwise, I'm going to get the one-sided, and we're going to be focusing on that two-sided confidence intervals here. All right. So if I go back to my notes here, I have this confidence interval here, and then we can provide this interpretation here. It says we are 95% confident that the true difference in the average miles driven between diesel and gasoline-fueled buses is between those two values that are in my confidence interval, negative 26 to about 13, right? 12.695. And so what this means, because both of these, my bounds include both positive numbers and negative numbers. So think about a number line that starts at negative 26.245 and ends at 12.695. It includes both positive and negative numbers. And this confidence interval is related to the difference between those means and what we expect those means to be in our population. And so in our population, we may have some negative differences, right? Well, in order for a difference to be negative, that means that the second term in that subtraction has to be larger than the first term in that subtraction, right? Well, the second term in our subtraction is the population mean for gasoline. So when I see negative values, that means that gasoline buses can drive upwards of this is the smallest negative number we have, at most 26.245 miles more than the diesel powered buses on average. That's coming from the negative value here. Now, our confidence interval also includes positive values, right? And in order to do a subtraction, when your subtraction yields a positive number, that means your first term in that subtraction is greater. And when the way we did our subtraction was to do diesel minus gasoline. So that means this confidence interval is also saying that diesel buses can drive at most 12.695 more miles than the gasoline buses on average, right? And so you can tell, because we have both positive and negative values here, this test, if we were thinking about this in terms of a test, is kind of inconclusive because our confidence interval has values that indicate that either the diesel buses can travel further on average compared to the gasoline and vice versa, right? This is why I kind of want to see my two-sided confidence interval because it gives us kind of a specific range where we'd expect our population parameter could possibly be within with 95% confidence. All right. And this is the interpretation or the format that I can create in APA format, or how I can write my confidence interval in APA format. So the 95% confidence interval for the difference between means was negative 26.25 to 12.70. All right. And so the field is moving more toward reporting effect sizes and reporting these confidence intervals, right? And we want to report these confidence intervals and effect sizes because when we have significant results, it doesn't give us a lot of information on the practical significance of those results, as well as some actual values that we expect our population parameters to be. All right, we're just saying if we were to reject the null hypothesis, is that it's greater than a value, it's less than a value, it's not equal to. It doesn't give us enough information regarding the potential values that we may have and the importance of those values. All right, and so we want to be able to interpret or include those in our interpretations as well. All right, and so I'm going to stop in this video. This is definitely make sure you do the practice problems because I looked at one example by going through all of these different concepts. You'll see some practice problems where you may get a significant result. You'll see different type of hypotheses in different contexts where you may have to interpret slightly different depending on the result of your significance test, the size of your effect, and then looking at your confidence interval. All right, but I'm going to stop here in this video, and then next we'll get to our paired sample t-test.